Hi. So in the next couple videos, we're going to be talking about the processes that happen inside the Earth. As you watch, keep in mind a couple things. Number one, make sure you're taking good notes. Number two, always remember the beauty of self-paced notes is that you can stop, rewind, or pause as needed. Number three, remember that your scores are part of your grade. And number four, make sure you get all the way through. If you have any questions, always come see me when you get back to class. Okay, let's dig in. Plate tectonics explains the phenomena associated with the interaction between the crust and the underlying mantle. Most likely you already have a basic understanding of it from earlier in this class as well as earlier in your schooling. Before we can get into the nitty-gritty of the theory, there are several things we need to talk about first. The first of which is continental drift, which is a very related idea. Continental drift is the idea that parts of the Earth's crust slowly drift on top of a liquid layer, or at least a semi-liquid layer underneath. It proposes that the position of the continents has changed over time, and that at one point they were in different locations altogether. The mass created by the continents all being together are called supercontinents. Okay. Supercontinents can include all of the land masses that exist, like Pangaea, what you've probably heard of. They can also include portions of land masses. So, for example, Laurasia described the landmass made when North America and Eurasia were one. Continental drift proposes that the continents that were all together have drifted to their current location. It's unknown who first proposed the idea of continental drift. Likely it was somebody who made maps way back when, and they noticed that certain pieces like South America and Africa seemed to fit together. But Alfred Wegener in 1912 was the first person who provided any kind of evidence for it. He had actual data and actual evidence, and was the most abundant amount of evidence that anybody had done so far. However, he was greatly admonished by his peers and by other people in the scientific community because first off, it seemed like such a ludicrous idea that the land moved. It seemed like a very fixed thing. Additionally, although he could provide some evidence, he didn't have any kind of mechanism to support how such a crazy thing would occur. So he never really got credit during his lifetime for the accomplishment because most people kind of laughed him off the stage. A lot of people, though, took notice of his evidence and thought there was something there. And over time, the idea of continental drift has been tweaked and refined with additional information and additional mechanisms proposed and tweaked to make it a little bit more accurate. Alfred Wegener didn't have everything perfect. He did have a little bit of error. Alfred Wegener was primed to be the person that did it. He had a lot of background in various areas of science together, and he really scoured the evidence. He had a lot of data to put together. You looked at a lot of that data when we did your Pangaea lab. So what is that evidence? Before we go on, let's take a minute and make sure you've got all the notes and do a couple review questions. Because you had the lab experience, I don't want to spend too much time talking about the evidence. You should already have generated much of your notes from that experience. But we'll go over some of it. The first piece of evidence is the shape of the continents. Many of the continents look like they fit together like puzzle pieces, none more so than South America and Africa, although many have areas that they seem to match. South America and Africa seem to be a near perfect shape, although you'll notice there's some areas where they're not. Why is that? Well, there's a couple of reasons. Number one, the boundaries aren't exactly where we see. First off, there's been quite a bit of stretching and thinning as the plates have moved, as there's been weathering and erosion. For example, the Nile, which empties off in this area, has created a huge amount of deposition into the ocean as the Nile delta opens up and deposits all of its sediment. Additionally, the plate boundaries aren't exactly the same as the land masses, and so even though the land doesn't seem to fit exactly, it's pretty darn close, and the plate boundaries match up really nicely. Another piece of evidence are the fossil records. Wegener found lots and lots of fossils, well, 4 at least in particular, that were found on different continents, and he couldn't propose any mechanism by which these organisms, which are all land organisms, could have gotten across the span of the Atlantic Ocean. For example, if we look at the Mesosaurus has 2 range that seem to match up almost identically in both South America and Africa. If we look at the Glossopteris, which is a fern, fossil records of a fern were grown in Antarctica. Antarctica, being cold, would never be able to support fern life. So one problem was, well, how did this fern survive in Antarctica? The answer is it hasn't always been in the South Pole. Another issue they found was this fern, the Glossopteris, was found in South America, Africa, Madagascar, India, Antarctica, and Australia. In this long swath that you see in that pink, and that swath can only be explained where that distribution of a fern could be is if the oceans weren't where they are now, and if they were much smaller, and those land masses were all closer, so that fern could naturally spread its offspring across that swath of land. Rock formations, too, provided evidence for Wagner. He looked at the Mauritania Atlas Range and the Appalachian Range, both of which are really old and can date back as far as the Paleozoic era, when Pangaea was first forming. So one can imagine that North America crashed into Africa, pushing those mountains up. Both the Cape Fold Belt is another mountain range that seems to match up as if they were once together. Another piece of data that Alfred Wegener was able to use were mineral and rock deposits that, once again, when you put the continents together the way they were in Pangaea, all seem to line up. A great example would be the gypsum that's found across North America, Greenland, and Russia. Finally, glaciation. We see two things when we look at Antarctica. Number one, we know that Antarctica is covered in glaciers now, but the ferns say that they haven't always been. Another thing that tells us is that we see glacial patterns in Africa, South America, India, and Australia, all places whose climate is very, very different than it is today. And those glaciation patterns, as if there was one massive glacier covering that whole area, suggesting once again that they were all together. So all that evidence supports the idea that there was one supercontinent that composed most of the land that exists today. That was the most recent supercontinent that did compose all of the land. However, we do know that think that when Pangaea broke up, it broke up into two smaller supercontinents: Gondwana, which made up the southern hemisphere continents, and Eurasia, which made up most of the northern hemisphere continents. We think it looked something like this as they moved apart. There were a lot of things standing in the way of Wagner's theory becoming accepted by the scientific community. We already talked about just the sheer craziness of it, that people just thought it was too wild to believe. Additionally, he did his work both before and after World War I. As a German, Wagner wasn't looked upon very highly after World War I, so he was battling some pretty big opposition. Scientifically, there were also some pretty valid reasons that people questioned it. A lot of it was that he had no explanation for how it happened. He proposed a couple of things. He talked about possibility of the Earth rotations or tidal forces being involved. He talked about the possibility of continent crust bursting through ocean crust and just some things that were kind of sketchy. And he even admitted that he didn't know. So he didn't have his mechanisms. And additionally, the mechanisms that were needed to explain continental drift weren't discovered until the 1950s, after sonar was used. That's called seafloor spreading. We'll talk about it in a later video. He had a few errors too. He didn't quite get right how different types of crust came to be. And finally, he studied, like I said, both before and after World War I. And as a meteorologist and an astronomer and a geologist, one of his main areas of study was Greenland. He actually died in Greenland, being an explorer, undergoing scientific studies. Anyway, as he was researching, one of his goals was he thought he might be able to observe Greenland moving away from Europe by charting the stars. People tried for a little while after his death too, and they were never able to observe it. Interestingly and kind of cool, now we can. So one thing we can do is that we can map very, very precisely with GPS from space the positions of objects, markers that we've put on Greenland, and we've seen that they in fact are moving away from Europe. And further, as I mentioned, Du Toit and Holmes came and refined some of his work. They proposed a mechanism and fixed some of the errors that he had. And most importantly, we started to understand seafloor spreading and get evidence for it. And seafloor spreading led us to the accurate mechanism for how plates move. We'll talk about that in our next video. Make sure you click all the way through to the end, and you come see me if you have any questions.